In our next section, section 2, we're going to start taking a close look at the beginnings of logic as a form of study, of a form of reasoning. And the first term that comes to mind when talking about logic is a conditional statement. And we'll see that with the related statements that you can come up with when you're confronted with a conditional statement. So first of all, a conditional statement is any statement that can be written in if-then form. If something, then something else. So the second part is always conditioned on what happens in the first part. So we'll take a look at some examples of that. So here's a example of a conditional statement. It's in if-then form, but they don't always become stated exactly in if-then form. What if I'd say, I'll play golf Saturday if it doesn't rain? It's still a conditional statement, but it doesn't come exactly in that form. You don't see the word then, and the positions are switched, but the condition part would still be whether or not it rains. And then the action that will happen will come depending on what happens with the rain. So the condition part is the rain, and then the action is playing golf. And there's a phrase for each of those. Whatever follows, when you have it in if-then form, whatever follows if is called the hypothesis. That's the hypothesis. The rain, Saturday. And the conclusion, whatever comes after the then, is called the conclusion. So it doesn't matter what order they come. Like I just said, it could have been, I will play golf if it doesn't rain. It doesn't change the fact that I will play golf is the conclusion, and the hypothesis, the condition part, is the rain on Saturday. In fact, when working on these kinds of structures, it's best to reword whatever statement you have. If it's not specifically in if-then form, then to reword it so that it is, and it makes sense. It makes the same sense as the original statement in if-then form. So you can easily pick out the hypothesis and easily pick out the conclusion. Now, when we're talking just in general, we can talk about the hypothesis or the conclusion. Here we've got a specific hypothesis and a specific conclusion. But generally speaking, we just make reference to the hypothesis as some clause P. And the conclusion is some clause Q. And logically, we just write that as this statement right here says, in logic language, in the symbols of logic, if P, then Q. That's the conditional statement in general. If P, then Q, written with those symbols. P is the hypothesis, Q is the conclusion. Your turn for a little practice. Read this statement, this conditional statement, and determine what is the hypothesis and what is the conclusion. Well, how'd you do? Let's see. As I mentioned, it's probably best to take a look at this thing in the proper if-then form. So to restate that in if-then form, it would say something like, if I earn a 3.0 this school year, then I will get my license. And the hypothesis would be, I earn a 3.0 this school year. Doesn't include the word if, does not include the word then. The conclusion is, what will happen is, the action is, I will get my license this summer. So that's a good example. Have a look at this statement, all dogs are canines, and let me know, is it a conditional statement or not? I don't see the word if and I don't see the word then, so it can't be a conditional statement, right? Wrong. It can be. And in fact, it is a conditional statement, and I'd like you now to write it as an if-then form. Write this conditional statement in if-then form. Once you've got it written in if-then form, finding the hypothesis and conclusion is a snap. So what is this statement in if-then form? I hope you wrote something like, if an animal is a dog, then it is a canine. The hypothesis, an animal is a dog. The conclusion, the dog's a canine, the animal's a canine. That is a conditional statement. So let's see about some other conditional statements that can be formed. If a given conditional statement, if P then Q, if you have one of those and you switch the hypothesis and the conclusion, you would have the converse. If Q then P. Let's see what that looks like as an example. Let's go back to the one of the first examples. If it doesn't rain Saturday, then I will play golf. The hypothesis, it doesn't rain. The conclusion, I play golf. So the converse of this statement would read something like, if I just switch places, whoops, the conclusion goes into the hypothesis position, the hypothesis goes in the conclusion position, it would read something like, if I play golf Saturday, then it didn't rain, or something like that. Okay, you might have to adjust the language a little bit so it doesn't make sense. You can't just say, if I will play golf, then it doesn't rain Saturday. That sentence doesn't make sense. So you alter the language just slightly so you get the main idea across. If I play golf Saturday, then it didn't rain would be the converse of this conditional statement. The next related conditional statement related to a original conditional would be the inverse of a conditional statement. This little squiggly line in front means not. If not P, then not Q. Not P, then not Q. We negate the hypothesis and negate the conclusion. So take that original conditional statement and see if you can come up with its inverse. Well, I don't know what you wrote, but if you negate the hypothesis, doesn't rain, what's the negation of not raining? The negation of that would be it does rain. And then what is, if you negate I will play golf, okay, the negation of will play golf means you won't play golf. So that inverse statement would read something like, if it does rain Saturday, then I will not play golf. The inverse. And the last related conditional statement to a given conditional would be a negation of the hypothesis and the conclusion, and also switching places. Okay, so the negation, oops, that should go here. These should both go in front. Okay. If not Q, then not P would be a contrapositive. Switch places, the hypothesis and conclusion switch, and they both get negated. So with that in mind, see if you can write the contrapositive of this given conditional statement. Well, if I switch the hypothesis and conclusion and negate them both, and then work the language a little bit so I'm not making some sense, you should come up with something that reads like, if I don't play golf Saturday, then it will rain. That's a negation of the conclusion and a negation of the hypothesis. And they've switched places. Now the next definition, or the next term I want you to hear is not really a new conditional statement. But if a conditional statement, if P then Q, is a true statement, and its converse, if Q then P, is also true, then both of those can be combined in a single statement called a biconditional statement. A biconditional statement is if the statement and its converse are both true. And you can write a biconditional, and the word we use is if and only if. P, if and only if Q. And since they're both true, you might say Q, if and only if P. And we'll see some examples of that as we go. Okay, let's examine this. I want to let the hypothesis be the value of x is -5. And I want to let the conclusion be the absolute value of x is 5. Now with that, can you write the conditional statement? Can you then write this is if Q then P. This is the converse, right? The converse. Is this a biconditional statement? Well, the three related conditional statements are: if the value of x is -5, then the absolute value of x equal 5. That's the A part. Put it into words. What were some symbols? The B part, write the converse. If the absolute value of x equal 5, then the value of x is -5. Okay. And then the biconditional statement would be something like the value of x is -5. And this is not a misspelled word. That's the way we represent if and only if. Instead of having to write that all the way out, mathematicians use this symbol IFF, usually italicized, to say if and only if the value of x is -5, if and only if the absolute value of x equal 5. Is that a true statement and a true biconditional? Well, no. I mean, since B part, if the absolute value of x is 5, the value of x is -5, is a false statement. And its counterexample would be, how about x equal +5? Okay, there's a counterexample. It makes the hypothesis true, but the conclusion is false. So that's a counterexample that proves to be false, so we can't have a biconditional, since the statement and its converse are not both true. It's important to know that if a conditional statement is true, well, let's just say that a conditional statement and the contrapositive are logically equivalent. So as we move forward, it may be difficult to prove a conditional statement is true. But if we can prove that its contrapositive is true, it's like proving the statement. For example, if the car will start, then the battery is charged. The contrapositive would be, if the battery is not charged, then the car will not start. And they're logically equivalent, so sometimes we can wrap our mind around the contrapositive and prove it to be true, and it would be equivalent to proving the statement. Likewise, the converse of a statement and the inverse of a statement are also logically equivalent. But we won't try to prove these anyway, but it's also, it's interesting to note. All conditional statements are either true or false. And this is a Venn diagram. Venn diagrams use sets and pictures of sets to represent the elements. And so we construct a true conditional this way. If you're an element of P, then you have to be an element of Q. So if P, then Q is a true statement represented by the Venn diagram. And so it might be helpful when constructing if-then statements or conditional statements to verify their truth values, to construct a Venn diagram and see if it works. Let's consider this conditional statement. If you play hockey, then you are tough. So the hypothesis is you play hockey, and the conclusion is you are tough. So if you're in P, if you play hockey, then you are tough. Let's take a look at the converse. If you are tough, then you play hockey. Okay, the converse would be this. If you are tough, then you play hockey. Well, the set of all tough people, instead of maybe you're an MMA fighter, or maybe you play football, or maybe you're a tough guy who doesn't play any organized sports. So you can be tough and not play hockey. So the truth table would be, this is true, but the conclusion of this statement would not be true. Let's take a look at the inverse. The inverse would be, if you don't play hockey, then you are not tough. So if you don't play hockey means you're outside of that group, then you're not tough. Well, you could be outside of that group and still be tough. So that would be a false statement. And then the contrapositive, if you're not tough, then you don't play hockey. So if you're not tough, means you're on the outside of the orange circle. You can't even get in there. If you're not tough, then you can't play hockey. You can't possibly get in the green circle if you're not even in the orange circle. So it is also true. The contrapositive is true. And using the Venn diagram helps with those types of um, truth tables, truth values. And that's where I'm going to leave it right now. We'll pick it up again tomorrow, and I'll give you your assignment in class.